Today's topic is telescopes, obviously a subject of great importance in astronomy. The basic idea of how a telescope works is that you have to have some kind of optic, either a lens or a mirror, that will focus light and make it come together, make it converge to make an image. So that would be either a convex lens or a concave mirror. That image is then recorded on film or a CCD chip or sent into an eyepiece for you to directly put your eye and look at it. The picture down here in the lower right is a CCD chip that is the heart of most astronomical research cameras. So we have a choice, either a concave mirror or a convex lens. Telescopes that use concave mirrors are called reflectors, and they take light from a distant source, those parallel light rays, and make them converge because the mirror is curved. Each ray is following the law of reflection, but because the mirror itself is curved, it makes the rays converge. The distance from the center of the mirror to where the initially parallel rays cross is called the focal length. The other choice is to use a convex lens to make the telescope for that first thing that converges the light. And so telescopes that use a lens rather than a mirror are called refractors because lenses work by refraction. So, and just like before for the mirror, the distance from the center of the lens to where initially parallel rays cross or converge is called the focal length, f. There are many, many different kinds of telescopes. I'm asking you to know just the three most basic kinds. First off, already mentioned, refractors use a convex lens. Usually that's called the objective lens because it's at the end of the telescope that's closest to the object. And the eyepiece at the other end, if you're using an eyepiece instead of a camera, the eyepiece serves as a magnifying glass to look at the image created by the objective lens. So refractors, there's a common misconception that Galileo invented the telescope. He did not, but they were invented. There are several people who are sort of in the running for having invented the telescope, but it was about the year 1608 in Holland. Reflectors use mirrors, and there are two kinds of reflectors, the most basic reflectors. There are two kinds. And so the concave mirror, here and here, okay, those are called the primary mirror. And you have light coming from the sky. I forgot to show you the animation for the refractor. And then here's light coming in for the first reflector. This is called a Newtonian reflector. So light comes down the telescope, hits the primary mirror, the rays converge. Now the problem is, if you allowed the rays to converge over here, you could put an eyepiece or a camera right here, but the problem is that your head or the camera would be blocking light from getting to the primary mirror. So we have this small mirror called a secondary mirror that deflects the light. It's a flat mirror, deflects the light 90 degrees out to the side where you have an eyepiece or maybe a camera. So this is called a Newtonian telescope, named after the person who invented Isaac Newton. And the third kind of telescope here is called a Cassegrain reflector. So we have light coming down the tube. It comes to a focus, or it's being converged, but before it actually comes to a focus, it hits a secondary mirror. This one is not flat, it is actually curved, and sends the light back down the tube to the right in the diagram. And the primary mirror, unlike in the Newtonian telescope, the primary mirror of a Cassegrain telescope has a hole in the middle. And so light goes through the hole and enters the eyepiece or the camera, whatever it is you have down there. So here are pictures of three telescopes. What kind of telescope is each one? Is there a refractor? Yes. The refractor is the one with Jack Black. The Newtonian reflector is B, and the Cassegrain reflector is C. Just to point out, there's that hole This is the MMT Observatory in Arizona, 6.5 meters across. It's more than 20 feet across is that primary mirror, and there's the donut hole. The secondary mirror is right here. Here's a Newtonian reflector. Here's an eyepiece. And this little thing here is basically an aiming device. We call it a finder scope. It has crosshairs in it, just helps you aim the telescope. So almost all large research telescopes are reflectors. And the question is why? And there are a couple of reasons, but the big one is that mirrors can be made larger than lenses. Lenses can only be supported around the edge. So if you have a piece of clear glass and light has to go through it, you can only hold it at its edges. Whereas mirrors, light doesn't go through the mirror. Light reflects off. So you can make a big mirror and you can support it all across the back. Also with a mirror, you only have one surface that needs to be ground to the proper shape and polished and coated. Whereas a lens, you have to grind and polish two sides of the lens, and that's labor intensive and expensive. And then lenses also have an issue called chromatic aberration. Lenses act a little bit like prisms because the sides are angled in. So a lens, just a single glass lens, will separate the red light from the blue light and the colors in between, and that will produce a color distorted image called chromatic aberration. Now there are ways of making lenses to minimize that with different kinds of glass and having more than one lens cemented together. Made out of different kinds of glass. So it can be minimized, but it can never be completely eliminated. And so the advantage there, again, goes to reflectors because mirrors reflect all light, all colors of light the same. They don't care. The one disadvantage that reflectors have is that secondary mirror. And light, when it passes the secondary mirror, and also the structures that hold the secondary mirror in place, will cause diffraction. And that diffraction will cause a little bit lower contrast in the image. And also on the images of stars, if you've seen images of stars with spikes in them, then that is caused by diffraction. So generally the largest research telescopes in the world are all reflectors. The largest telescope mirror in the world is 8.4 meters in diameter as far as a single piece. And the largest lens, objective lens for a refractor was 1 meter in diameter. And there are larger telescopes, 10 meters and above. And there's some under construction right now, up to 30 meters, I believe. But those telescope mirrors are all made by joining pieces together like tiles. So the largest single piece mirror is 8.4 meters in diameter. So here's a breakdown. Disadvantages of refractors: they're more expensive, less compact, chromatic aberration, and because they're smaller, they can't gather as much light. Whereas reflectors, however, cannot see space vampires. This, by the way, is an XKCD cartoon. If you're not familiar with XKCD, look it up. What do telescopes do? Why do we want telescopes? 3 basic reasons. Magnification, which is actually the least important, to collect lots of light and to improve the detail, what we call the angular resolution that we can see. So angular magnification is the ratio, how many times larger the object looks when you look in the telescope compared to if you just look with your eye up at the sky. So here I'm talking about a telescope with an eyepiece, and you're actually looking through it. So the angular magnification is how big, if you put your eye to the eyepiece, how the angle that object, let's say you're looking at the moon, the angle the image of the moon makes at your eye compared to if you just look up at the sky without the telescope. The ratio there is the angular magnification. So for a telescope with an eyepiece, it turns out that that ratio is the same as the ratio of the focal length of the telescope, which means everything other than the eyepiece, divided by the focal length of the eyepiece. I have a Newtonian telescope that is 150 millimeters in diameter with a focal length of 1200 millimeters. I have 4 eyepieces, 10, 20, 30, and 40 millimeters focal length. My question to you is, which eyepiece would I use to get the highest magnification? Go ahead and hit pause as you think about it. The answer is 10 millimeters because the magnification is the focal length of the telescope divided by the focal length of the eyepiece. The magnification is inversely proportional to the focal length of the eyepiece. So the shortest focal length eyepiece will provide the highest magnification. Same telescope. If I put in the 20 millimeter eyepiece, what will the magnification be? Again, hit pause. The answer is 60. The focal length of the telescope is 1200 millimeters, and we're dividing by the focal length of the eyepiece. So 1200 divided by 20 gives us 60. The diameter of the telescope does not matter. All that matters is the focal length of the telescope and the focal length of the eyepiece. On to the next function of a telescope, and this is really probably the crucial one of the three, although all three are important to some degree. But telescopes serve, astronomers like to use the phrase a light bucket. They collect lots of light. When you look up at the night sky, just with your eye, the only light you perceive is the light that happens to hit the pupil of your eye. With a telescope, you can have a large diameter, many meters across, and you're collecting lots of light. Most telescopes have a circular aperture, so the size of the target, the bucket, if you will, that the light has to hit in order to enter the telescope is the area of a circle. Area of a circle is pi r squared, or if you write it in terms of the diameter, pi times the diameter squared over 4. So a quick example. There are 2 telescopes on Mauna Kea in Hawaii. They're called the Keck telescopes. They're 10 meters in diameter. How much more light does one of the Keck telescopes collect than your eye? Let's say the pupil of your eye is 5 millimeters across. So we can do the calculation. The area of the Keck, pi times 5 meters squared. I'm using pi r squared. These are 10 meters in diameter, so 5 meters in radius. So pi r squared gives us about 80 square meters. The area of your eye, pi r squared, we said 5 millimeters. So that's 2.5 millimeters, but we have to put it in the same unit. So we're going to put it in meters. So from 2.5, we're going to move the decimal point 3 places, 0.0025 meters squared. And when you punch that into a calculator, you get about 0.00002 square meters. And the ratio of those, the ratio of the Keck telescope to the eye, 80 divided by 0.00002 is 4 million. 4 million. Now there is a simpler way to do that calculation. Now this may not look simpler, but I want to show you the pattern, and then it'll be simple in the end. So the ratio, the area of the Keck over the area of the eye, pi r squared for Keck, divided by pi r squared for the eye. Well, the pi's cancel, and so we're left with the ratio of the radii squared. Well, the ratio of the radii is the same as the ratio of the diameters squared. If the telescope has twice the radius of another telescope, its diameter is twice the diameter of the other telescope. So for the Keck telescope, we can simply take 10 meters divided by 0.005 meters, 5 millimeters. That gives us 2,000, but don't forget that we're squaring that. So 2,000 squared gives us 4 million. Now I know that looks longer, but now you can just remember the basic rule is you take the ratio of the diameters and you square it. There's a lot on this slide. So the Keck telescope, we're saying, collects 4 million times more light than your eye. So all other things being equal, it can see objects 4 million times fainter than your eye. But all other things are not equal. First off, the CCD chips used in astronomical research cameras are about 90% efficient. That is, they respond to about 90% of the light that hits them. Your eye is only about 4 or 5% efficient. It doesn't respond to most of the light that hits it. The retina is actually not well designed. The light has to go through blood vessels before it gets to the light sensitive cells in your eye, in your retina. Your eye only responds to about 5% of the light. So CCD chips, if we take the ratio of those numbers, are about 18 times more sensitive than your eye. Your eye cannot store or record light. Your eye acts like a video camera, shooting about 10 frames per second or so. That's why a light that's flickering very, very fast, you cannot see it if it's flickering faster than about 10 or 20 times per second. That's why movies in the movie theaters are 24 frames per second. Your TV is usually 30 frames per second. And so your eye can take only, you can think of it like a camera taking 1/10 of a second exposure. Whereas a camera, you can open up and just expose the CCD chip or the photographic film. You can just expose it for hours at a time. For the purposes of this discussion, let's go ahead and say with a CCD camera, we open the shutter of the camera for 1 hour, 3,600 seconds. Then that 1 hour exposure is 36,000 times longer than one frame of your eye, if we think of the eye like that video camera. So really, the Keck telescope can see things that are 4 million times 18 times 36,000 times fainter than the human eye, and that's about 3 trillion. So you can see why astronomers want big telescopes. It's not just about bragging rights, it is about seeing fainter things. If you can collect more light, you can see fainter things, which means you can see farther away. You can see smaller things that are dimmer. And if you're a cosmologist, someone who studies the history of the universe as a whole, if you can look farther away, you're looking back in time, because light takes a lot of time to travel across the universe. If you're looking at a galaxy that's 5 billion light years away, you're looking at it as it was 5 billion years ago. And so the bigger telescope you have, the farther away you can see, the further back in time. My Newtonian telescope that I've mentioned already, how much more light does this telescope collect than my eye? And let's again assume a 5 millimeter diameter for the pupil. Go ahead and pause, think about this, and come back. And the answer is 900 times. Here is the diameter is what matters, not the focal length. 150 millimeters is the diameter of the telescope. 5 millimeters is the diameter of the pupil. So 150 over 5 gives us 30, and 30 squared is 900. And the last of our 3 functions of a telescope is improved angular resolution. That is, being able to see finer detail. Smaller angular resolution is better. The human eye with good vision has a resolution of about 1 arc minute. I just want to remind you that an arc minute is the word we use for 1/60th of a degree. An arc second is 1/60th of an arc minute. Therefore, it's 1/3600th of a degree. So just reviewing that vocabulary. So the human eye can see about with a resolution of about 1 arc minute. We can't see the surfaces of the stars. They are too far away from that. The size of the dot of light formed by a telescope, big telescopes, the size of the dot created is determined by 2 things. Diffraction, which we've talked about a little bit, and seeing. But let's go into a little bit more detail. Oh, this, by the way, is a little activity for you to do where you can measure the resolution of your eye. So if you want to do this activity, go ahead and hit pause, and you can determine the resolution of your own eye. But I'm going to move on. Diffraction. Remember, diffraction was the spreading out of light when it goes through a hole or past a barrier. Well, a telescope is a hole. It's that bucket. And when light enters, even a refractor, even without a secondary mirror, the light will diffract. And it's a little bit worse with a reflector, where you have that secondary mirror and the structures, the support veins that hold up the secondary mirror. So here's an image of a star, highly magnified. It's a bright star, and you can see these spikes in the image. Those are not actually part of the star. Those are an artifact, a byproduct of the telescope itself. Resolution is fundamentally limited by diffraction of the light entering the telescope. If you zoom in on the star enough, its image will look blurry. If it's a good night with not much turbulence in the air, you will see rings around the image of the star. And here is an actual image of a star with those rings around it. Up here, these are just kind of idealized. If two stars are close to each other, that is, if we have a binary star, their blurriness can overlap, making it impossible to tell that there are two stars instead of one. The resolution of a telescope can be calculated with this equation right here, that theta min, the smallest angle that can be perceived, is about 250,000 arcseconds times the ratio of the wavelength of the light divided by the diameter of the telescope. What this tells you is that larger diameter telescopes, because it's on the bottom of the fraction, give you better resolution. Remember, a small number is better. So bigger d gives you a smaller theta, and that's good. And shorter wavelengths produce smaller theta, a better resolution. Now, that preceding equation for the resolution of a telescope was ignoring turbulence in the Earth's atmosphere. And turbulence in the Earth's atmosphere is what astronomers call seeing. It is, an analogy would be if you were in a swimming pool, you're wearing goggles and you go under a swimming pool and you look out at someone standing at the edge of the pool, then they're going to look all kind of shimmery. In the nighttime sky, this is what we call twinkle. You know, the old song, Twinkle, Twinkle, Little Star. Stars, for the most part, don't actually twinkle. It's the atmosphere's fault, our atmosphere's fault, that causes the stars to twinkle. And again, astronomers use the term seeing to refer to this. This animation is showing highly magnified the image of a star as it jumps around. So the Earth's atmosphere is causing it to jump around. It's also breaking up the image into, if you look inside that moving blob, you see that there are little blotches inside of it. So if the telescope that made this image were not at the bottom of our atmosphere, but was instead in space, just above the atmosphere, then the image would be the size. First off, it wouldn't be jumping around all over the place, and the image would be the size of one of those little blotches inside the big blob that's moving around. With our telescopes in the Earth's atmospheres on the surface of the Earth, generally we are limited to a resolution of about 1 arcsecond or so. The very best observing sites, you might get a half or a third of an arcsecond. But a 1 arcsecond is a good ballpark number for the resolution of a telescope on the Earth's surface due to turbulence in the Earth's atmosphere. Here are a couple more animations, or actually videos of the left-hand one is a star, just the image. It may actually be a binary star, I'm not sure. And then the image on the right, the video on the right, is a crater on the moon. Again, highly magnified so that you can see the blurriness and the changing of the blurriness due to turbulence in the atmosphere. There are some solutions to seeing. The simplest solution in a conceptual way is simply to take your telescope and put it in space above the atmosphere. Some people may think putting a telescope in space gets it closer to the things you're looking at. That's not why it's a good idea to put a telescope in space. You're simply eliminating the blurring effects of the atmosphere. It being a couple hundred miles up in the sky doesn't make it significantly closer to anything. But it does eliminate the blurring effects of the atmosphere. Now, when I say that is a simple solution, it's conceptually simple. Technologically, it's hugely complicated and really, really expensive. So this is a picture of the Hubble Space Telescope, and this is a picture of a mock-up of the James Webb Space Telescope that is the successor to the Hubble Space Telescope that is due to be launched in 2020. It is under construction. It has almost been completed. They just have a few last things to do, and it should be launched in 2020 is the goal. The other solution to seeing is what we call adaptive optics. Oh, I forgot. Here's another reason for putting telescopes in space before we get to adaptive optics, is that the Earth's atmosphere is not transparent to all wavelengths of light. It's transparent to visible light. And so this graph here is the fraction of light that is blocked and as a function of wavelength. And at the top here are the different parts of the electromagnetic spectrum. The wavelength here at the bottom is in units. These are angstroms. An angstrom is 1/10 of a nanometer. But here are X-rays and ultraviolet at this end, and the atmosphere is completely opaque to these. X-rays and ultraviolet rays cannot get through the Earth's atmosphere because of ozone and oxygen in the atmosphere, molecular oxygen, absorb X-rays and ultraviolet, so they don't make it through. Visible light, however, obviously does. We can see the sun, we can see the stars. Visible light does make it through the atmosphere. Some gets absorbed, but most of it makes it through. Infrared is complicated. There are parts of the infrared spectrum, colors of infrared, to use that word, that are completely blocked, and there are other colors of infrared that make it through. So we call these infrared windows. Same thing in the microwave portion of the spectrum. There are microwave frequencies or wavelengths that make it through, others that don't. Radio waves, the atmosphere is completely transparent to radio waves, and so radio telescopes can be on the ground. But if you want to have a telescope that will receive and make images using X-rays or ultraviolet, you've got to launch them into space. And then there are also space telescopes that observe in infrared light to avoid all the problems here. We can also put telescopes on airplanes to get them above most of the atmosphere. This picture is SOFIA, the Stratospheric Observatory for Infrared Astronomy. It has a 2.5 meter diameter telescope in the back of it, and it's a joint project of Germany and the US. Okay, back to adaptive optics that I mentioned briefly earlier. Adaptive optics are a technological solution to seeing, where you put some kind of device in the telescope that counteracts, that somehow detects and counteracts the effects of turbulence on the light that pass through the atmosphere. This video clip that I'm about to start shows a star system, a multiple star system, with the adaptive optics system off at first, and then you will see the adaptive optics system turn on. It's actually a triple star system that without the adaptive optics you wouldn't be able to tell. There are 3 stars there. Here's another video clip of a telescope looking at the sun, actually. On the left is with no adaptive optics. Oh, sorry, on the left is with the adaptive optics, and on the right is without adaptive optics. Those patterns, by the way, are called granulation on the surface of the sun. They're basically convective bubbles of hot gas rising from the interior of the sun. So how do adaptive optics systems work? There's a lot of text on this slide. Feel free to hit pause to read it all. But the basic idea is that you have a camera that watches a star. And we know what stars are supposed to look like. They're supposed to look like an airy disk, which is the name for when you have that circular circular patch of light with the rings around it. That is the perfect image created when you are operating at the diffraction limit of the telescope. So the telescope has a system that looks at that image, camera that looks at that image, and then somewhere in the camera or in the telescope there's going to be a mirror that is flexible, a mirror that can change its shape, like a piece of paper, or a better analogy would be a thin rubber sheet. And glass, if you make it thin enough, if you make glass like the thickness of a piece of paper, it is actually flexible. And so you can put little actuators behind a mirror that is flexible, computer-controlled actuators that will change the shape. And so you take the light beam that's been collected by the big mirror of the telescope, and you have it bounce off this flexible mirror whose shape can be controlled by a computer, and that computer is controlling the actuators based on what it sees from a camera. Here is an animation that shows schematically how one of these systems works. Here's an observatory. It's going to peel away so we can look at the telescope itself. Real quick, what kind of telescope is this? If you said a Cassegrain telescope, you are correct. There's a donut hole in the big mirror. Here's light coming down from the sky, hits the secondary mirror through the donut hole into the adaptive optics system on the back of the telescope. We peel away that. Light gets deflected, it's split, and there's a science camera and the adaptive optics camera. There is the image of the star, and here come the wavefronts from the sky. Notice that they look crinkled. And this is to simulate turning on the adaptive optics system. There's your flexible mirror. The flexible mirror is changing its shape in real time to correct for the turbulence of the Earth's atmosphere. Real adaptive optics systems change the shape of that flexible mirror up to 100 or 200 times per second to correct turbulence in the Earth's atmosphere.